Okay, for question number 1, we want to find out how many different elements are in the compound. We have sodium, carbon, and oxygen. It doesn't matter how many of them there are. We just want to know is how many different elements. So there are going to be 3. For question 2, same thing. We want to find out how many different elements are present. We have nitrogen in 2 different places, so that will only get counted once. And then we have hydrogen and oxygen. So again, we have a total of 3. Question 3, the simplest whole number ratio. Another way of saying simplest is reduced. It is the most reduced formula you could possibly have. There is not a number other than 1 that could divide into it. This is not something we've learned about. This is not something we've learned about. And then you need to know the reduced form is the empirical formula. The molecular formula will show you what it really looks like. For question 4, we're told that we have a ratio of 2 atoms of nitrogen, so you'll have 2 nitrogens, with 1 atom of oxygen. So we'll just put that together using our subscripts. So we have 2 nitrogens. We usually won't put a 1 for a subscript, but we have 1 oxygen, and that matches choice B. For number 5, we want the empirical formula. So again, we want the reduced formula, the one that only the number 1 can divide into the subscripts. So we look at choice B, we could divide both of those by 2. Choice C, we could also divide them by 2. Choice D, we could divide them by 2 or 4. So that means that A is the only one you cannot reduce. That is your empirical formula. Same process on number 6. We want the empirical formula. We could divide this by 2, divide this by 2, divide this one by 2. This is the only one with only 1 oxygen here at the end. We could not reduce that. Okay. We are going to take our molecular formula and to find the empirical formula, we will reduce it. What number can divide into both 4 and 10? We can divide them both by 2. So you have 4 divided by 2, we'll get 2. If we have 10 divided by 2, we'll get 5. So we'll have P2O5. And that goes with choice C. And that was for question number 7. Number 8. Again, look at these numbers. Think about what number could divide into all of them. We could divide them all by 2. So if you divide 4 by 2, we get 2. If you divide 2 by 2, we get 1. If you divide 4 by 2, we get 4. So those are the new subscripts, C2BR, there's just the 1, and then F4. And that is going to match choice B. Number 9, we don't have choices. We want to write the empirical formula for this molecular formula. The number that can divide into both of those subscripts is again 2. So when you divide 4 or 8, let me start over. When we divide 8 by 2, we're left with a 4. We divide 18 by 2, we're left with a 9. And that would be our empirical formula. For number 10, the largest number that can divide into all of those subscripts is 6. We could divide by 3. We could divide them by 2. But then we would have to continue to divide. 6 is the largest one. So when we divide 6 by 6, we're left with 1. When we divide 12 by 6, we're left with 2. And when we divide 6 by 6, again, we have 1. But typically, we don't write the 1s for subscripts, so it's just CH2O. For number 11, we want to find which one of these molecular formulas would reduce to give us the empirical formula of CH2O. So we have to combine the different elements that are given on each one. So in choice A, we have 1 carbon. We have a total of 4 hydrogens, and then there's 1 oxygen. And we just have to set those up for each of our choices. So for choice B, we have 2 carbons. We have 3, 4, 5, 6 hydrogens, and we have 1 oxygen. For choice C, let's write them in the same order. We have 1 carbon. We have 2 hydrogens. and we have 2 oxygens. And then for choice D, we have 2 carbons. We have 1, 2, 3, 4 hydrogens, and then we have 2 oxygens. And we want to just pick which one would reduce to give us C2H or CH2O. Sorry, this formula here is what we're looking for. So in choice A, the only thing that's different is there's a 4 instead of that 2, so that cannot be it. If we reduce, we can't reduce B because of course there's only the 1 oxygen there, so that cannot be reduced. We can't reduce choice C any further, and it does not match. You have 2 oxygens instead of 1. So that leaves us with choice D, and if you took all of those subscripts and divided them all by 2, we would have CH2O, which matches the formula given in the problem. Okay. For question 12, we want to determine the empirical formula for the acid that's given, so we're going to do the same thing kind of backwards that we did on the last one. We start with the molecular formula and then we'll reduce it. So this one we have to combine quite a bit, so we're going to have CH3, and whenever you multiply the 14 by what's inside those parentheses, we'll end up with 14 carbons and 28 hydrogens. And then we have the COOH. So then we just need to combine it all together. When we count up our carbons, we have 1, 2, and 14. So that's a total of 16. For your hydrogens, we have 28, plus 3 gets us 31, plus 1 more gets us 32. And then oxygen, we have the 2. So we just need to reduce that. What number divides into all of those subscripts? We could divide them all by 2. So we're left with 8, 16, and 1. So we just find the one that matches, and that would be choice C. You have to be careful because choice D is what we came up with for the molecular formula, but it wanted to know the empirical formula, the reduced formula. Okay, number 13, we want to determine which of these choices would have the same empirical formula as glucose. So we divide each one of these by 6. So our empirical formula is CH2O. So we have to find which one would match. Choice A does not even have oxygen. It's not right. Choice C does not have oxygen. Cannot be right. So we just have B and D. We could divide 2 into each one of these, and we would be left with CH2O. It matches. So it would be answer B. We cannot reduce choice D because 11, it's a prime number. The only number that divides into it other than itself is 1. You cannot divide 11 into 12, so we cannot reduce that one in any way. We're on the second page. For question 14, we again have not talked about structural formula or ionic formula. So we have either A or D, and if we look at this, can you reduce it? If you cannot reduce it, if it's already the most reduced it could be, that's the empirical formula. If we could divide it all by something, like for example here, 2, that makes it a molecular formula. It's showing you what the molecule really looks like. For number 15, we have 2 different formulas. We have CH3 for formula A and C2H6 for formula B. And we can tell that we're thinking about empirical, molecular. We have to kind of see which ones we have. So CH3, is there a number that divides into 1 and 3 other than 1? And there's not. So that means that this one's empirical. Is there a number that divides into both 2 and 6? Number 2. So that means that this one is molecular. So they are different. They're not both anything. So we just have to match them up correctly. Formula A is the empirical one. Formula B is molecular. Number 16, we have 2 different compounds given, sucrose and ethanol. And we have the number of atoms. We have carbon, oxygen, and hydrogen. Sucrose is going to have 12 carbons, 11 oxygens, and 22 hydrogens. And that's in a different order than we're used to seeing it, but that's okay. We're just comparing these. For ethanol, we're going to have 2 carbons, 1 oxygen, and 6 hydrogens. So we want to find out which is the same for both of these. Would the mass of them be the same? If you have 12 carbons versus 2 carbons, would they weigh the same amount? And you have all of those differences. And we know when we look up those elements on the periodic table that the sucrose molecule would be much heavier than the ethanol. So the masses are not the same. The length of the molecule. If you have 12 plus 11 plus 22, that's a total of 45 atoms linked together versus 9 for the ethanol. Which one's going to be longer? The sucrose molecule is going to be much longer. So it's not going to have the same length. When we count up the number of atoms in each one of our molecules, we just did that. We're going to have 45 atoms in the sucrose, 9 in the ethanol. They do not have the same number, but they do all have the same types of atoms. They all have carbon, oxygen, and hydrogen. Number 17, we are getting into some of the calculations for finding empirical formulas. So remember, on all of these, when they give us percentages, we are assuming that we have a 100-gram sample. It could be any number, but 100 is nice to work with. So we can just take those percentages and change them into grams. So we'll list those, but we cannot compare grams of elements and figure out how they're pairing up, how they're bonding. So we have to divide them by their molar mass values on the periodic table. And that's how we're going to be able to compare them. Once we get them into moles, we can figure out how many more of one element we have than the other. When we write down our answers, if you just write it down about 4 places, then we will have plenty of numbers to compare. We're not cutting it off too soon, but we're not having to write everything in the calculator. And then at this point, when we've divided the values given by the value for molar mass that we get from our periodic table, we have the number of moles. So this is moles and this is moles. And we want to divide by whichever one is the smallest. So out of those two values, the smaller one is the 6.244. When you divide a number by itself, it will always equal 1. When we divide the bottom, again, when you put it in your calculator, this is the order you type it in, just left to right. We end up very, very close to the whole number 4. If you need to put yourself a little reminder here, we're looking over here and we're picking whichever one is the smallest. It goes over here. So this number at the end tells you how many you have of each element. Carbon, you're going to have 1. Hydrogen, you're going to have 4. So our formula is CH4. The one that matches is answer D. And the next few problems are very, very similar. They all have carbon and hydrogen in varying percentages. So on number 18, carbon's 85.7%. We just change it to grams. We'll divide it by the molar mass from the periodic table. Hydrogen is 14.3 grams divided by its molar mass on the periodic table. And I put the units on the first one, but we can kind of leave those off as we look through these next ones. But we'll end up with 7.135 and 14.15. We'll divide by the smaller number of moles. So the first one is 1. The second one is 2. You have 1 carbon and 2 hydrogens. The correct answer is B. For number 19, same setup. We have 92.3 grams of carbon, 7.7%. Whoop. Remember, we're changing percentages to grams. You probably remembered. We'll divide those by our molar mass values. We'll write down about 4 numbers or so. And we'll divide by whichever is smallest. So these are very, very close, but a smaller one is the value there for hydrogen. So we'll divide by the 7.623. So that one will be 1. And the top one, when you divide it, is also very, very close to 1. So our formula for the empirical formula is CH. Number 20, we're switching to different elements here. We have sulfur and oxygen now. Same process though. We start with 40 grams of sulfur, 60 grams of oxygen. Divide by molar mass values from our periodic table. We just type those into our calculator to find out how many moles we have of each. So we get 1.247 for sulfur and 3.75 exactly for oxygen. We'll divide by the smaller value. So for sulfur we get 1, and for oxygen we get 3. So our formula is SO3, which matches choice B. 21, we again have sulfur and oxygen. Sulfur this time is 57%, so we have 57 grams. Oxygen is 43%, so 43 grams. We'll divide by those same molar mass values. We won't have to look them up again. This will get us the number of moles that we can compare. We have 1.777 for sulfur and 2.687 for oxygen. We'll divide by the smaller number. So we have 1 for sulfur. And when we divide the values for oxygen, we do not get really close to a whole number. It's actually very close to 1.5. It's one of those common decimals. So the way that we can take care of that 0.5, because we cannot write SO 1.5, is to multiply by the smallest number possible to get a whole number. So if it ends with 0.5, the smallest number you could multiply to get a whole number would be 2. And just like in algebra, whatever you do to one side of your equation, you have to do to the other. Whatever we multiply one of our elements by, we also have to multiply the other. So we end up with 2 sulfurs and 3 oxygen. So instead of SO 1.5, we multiply each of those by 2, and we get S2O3. So out of our choices, that would be answer D. Number 22. We have boron and iodine, elements we haven't used much. Boron is 2.8%, so 2.8 grams, and iodine is 97. So we'll look up the molar mass values on our table. Boron is 10.81, and iodine is 126.90. When we divide those values, we get 0.2590 for boron and 0.7643 for iodine. We'll divide by the smaller quantity. We'll get 1 for boron and very close to 3 for iodine. So we have Bi3, and that will match choice C. You just have to be careful you don't put the 3 on the wrong value there. Number 23. Now we have 3 different elements. We have N, H, and O. Nitrogen is 43.8 grams, hydrogen 6.2, and oxygen is exactly 50.0. We'll divide nitrogen by 14.01, divide hydrogen by 1.01, and divide oxygen by 16. And when you divide those, for nitrogen we end up with 3.126. For hydrogen we get 6.138. And for oxygen, we get 3.125. The next step is to divide them all by the smallest, which is that last one. So that is going to be 1 here. When you divide nitrogen, it's very, very close to the same number, so you also get 1. And when you divide hydrogen, you end up with 2. So our empirical formula, remember this process gets you the empirical formula, is going to be NH.2O. If we read the problem, we want to find out which is a possible molecular formula for this substance. And you notice that none of them match because we don't want the empirical, we want a molecular formula. As you look at your options, there should be one that stands out as a completely incorrect answer, and that's choice B, because you cannot have an N as a subscript. Those are supposed to be numbers that are down here at the bottom. So B cannot be correct. For the others, you need to rewrite them to where you only have each element once. So on choice A, we have 2 nitrogens, we have 4 hydrogens, and we have 2 oxygens. For choice C, we have 1 nitrogen. We have a total of 4 hydrogens and 1 oxygen. For choice D, it's already split up by element, but we want to write it in the same order as our empirical formula, so we would rearrange it to N2HO. So we can see that choice D completely does not match with what we came up with. It looks close, but the numbers are not in the right place, so it cannot be D. When you look at choice C, if we multiplied the H in the middle times 2, we would get that 4, but it would also change the N and the O. You would also multiply those by 2 and get N2 and O2. So that was not done correctly. So that leaves us with choice A. If you did multiply each one of these here by 2, you'd get N2H4O2. So that is one of our possible options. A would be your correct answer. Number 24. We have calcium, carbon, and oxygen. We have 40 grams for calcium, 12 grams for carbon, and 48 grams for oxygen. We'll divide them by their molar mass values. Calcium, is 40.08. So when we divide that, we get 0.9980. Carbon is 12.01. When we divide, we get 0.9991. Both of those are very close to 1. And oxygen we'll divide by 16, and we get exactly 3. If you wanted to write 4 digits, it'd be 3.000. So now we'll divide them all by the smallest, which would be that top value for calcium. When we divide it by itself, we get 1. Carbon is also very, very close to 1. And when you divide 3 by that 0.9980, we get very, very close to exactly 3. So we have 1 calcium, 1 carbon, 3 oxygens, and that will match choice A. Number 25. These are a little bit different. We want to find the molecular formula when we're already given the empirical formula and we're given a molecular mass of the molecule, of what the molecule actually looks like. So we need to figure out what ratio we want to multiply our empirical formula by. And the way we calculate that is to take the molecular mass, which will always be given to you in the problem, and divide that by the empirical mass. That's going to be the molar mass of your empirical formula. Just take the CH2 and find out how much it weighs on your table. So molecular mass is given. It's 42 grams per mole. And when we look up carbon, we get 12.01, 2 hydrogens, 2 times 1.01, and we get a total of 14.03. That's the empirical mass that you divide by on the bottom. You should always end up with a number that's very, very close to a whole number. If you end up with a number less than 1, then you probably divided in the wrong order. I would try flipping them around and dividing it the other way. But when we divide that, we end up very, very close to the number 3. So that means that you're going to take your empirical formula here and just multiply each one of those subscripts by 3. So you end up with 3 carbons and 6 hydrogens, and that's going to match choice C. For number 26, same process, actually the same empirical formula even. We're just starting with a different molecular mass. This time it's 70. So remember, our ratio is molecular mass over empirical mass. We can kind of shorten it like that. So our molecular mass is 70. Our empirical mass, we already figured it out on the problem before. The 12.01 and the 2 hydrogens gave us the 14.03. So when you divide 70 by 14.03, you get really, really close to 5. So you take your CH2 and multiply every subscript there by 5. So you end up with 5 carbons, 10 hydrogens, and that would match choice D. 27. Now our empirical formula is CH4. Molecular mass is 16. So we have molecular mass over empirical mass. 16 over. This time we have a carbon, and 4 hydrogens for a total of 16.05. That's what goes on the bottom. Very, very close to exactly 1. So you don't have to actually multiply by everything. It stays the same. We have a molecular mass of 54. The empirical formula is C2H3. Molecular mass over empirical mass. So we have 54 over 2 carbons plus 3 hydrogens. We get a total of 27.05. When you divide 54 by 27.05, it's really close to 2. So you take your empirical formula, multiply every subscript by 2. C4H6. Choice B. 29, we have an empirical formula. We have a molecular mass of 58.12. Molecular mass over empirical mass. 58.12 over 2 carbons and 5 hydrogens. We get a total of 29.07 here. When we divide those, really close to 2. Take your empirical formula times 2, you get 4 carbons and 10 hydrogens. That would be choice C. For number 30, we do not have any answer choices. We're going to come up with the molecular formula all on our own. We have the empirical formula given. We have the molecular mass is 128. Same process. We have 128 on top. This time we have 5 carbons and 4 hydrogens for a total of 64.09. When we divide those, it's very close to 2. So we'll take each subscript times 2, and we end up with 10 carbons and 8 hydrogens, and that's our final answer. 31 is kind of shifting gears. We're going in the opposite process of what we've been doing. We're going to start with the chemical formula, and we are going to find the percent by mass of an element within that compound. None of these ask you to find the percent composition for every single element. We're just going to focus on a particular element in each one. And the first set of questions here is just asking you to set it up correctly. So remember, when we want to calculate percent, our formula is to take the part that we're looking for over the whole amount times 100. That's like moving your decimal over to the right twice. So the part that we want in this problem is carbon, and this is the whole formula. So we want the carbon, there's only one of them, over the whole thing times 100. So you go to your periodic table and find out how much those things weigh. Carbon weighs 12.01. These answer choices are rounded off to the whole numbers, so we can just put 12 for carbon on top. For the bottom, we have a carbon plus 2 oxygens. So when we do that math, we end up with 12 over 44 times 100 to change it from our decimal to our percentage. So we don't have to actually solve this yet. They just want us to pick the correct setup for this problem. Question 32 is asking us the exact same thing. What is the percent by mass of carbon and carbon dioxide? Only this time we want a real answer. So we already figured out the work. Our part over the whole times 100 is what we picked on that last question. We go ahead and just type that into our calculator, and we end up with 27%. In class, we learned that we would write these out to 2 places after the decimal. Some of these are rounded off to the whole number. You would solve them the exact same way. For 33, we want to determine the percentage by mass of hydrogen in this compound. So our part, we have 3 hydrogens. And if we wanted to write it that way, we could. Or we could write H3 like this also. and it will be over the whole amount times 100. So when we look up hydrogen, it's 1.01, or we can just do 1 times 3. And then for the bottom, we have 14 for nitrogen plus our 3 hydrogens. So we end up with 3 over 17 times 100. Okay. Number 34, we want the mass of nitrogen within the whole thing. So you need to distribute this 2 that's outside to everything in the parentheses. So in this formula, we actually have 2 carbons and 2 nitrogens. So if we want the part that's carbon, we're going to have N2 over the whole thing. So we'll go to our periodic table. Again, round these to the nearest whole number. And so we have 2 times 14. We'll have magnesium plus 2 carbons plus 2 nitrogens. And these numbers in parentheses are just the atomic mass values from the periodic table, or molar mass values, if we want to call them that. So whenever we type those numbers into our calculator, we are going to end up with 28 on top and 76 on the bottom, times 100 to change it into our percentage. So this is our setup. And be sure you pick the one that has the right numbers in the right places. Number 35, we're back to finding actual percentages. We want to find the percentage of oxygen in CO. So there's just a single oxygen over the whole thing. Oxygen weighs 16, 1 carbon and 1 oxygen. So when we do that math, we end up with 16 over 28 times 100. And when we round that to the nearest whole number, we get 57%. For question 36, we want to find the percentage of iron in the compound. So how many irons are there here? There are 2. So we're going to have 2 irons, and again, you can write it in front, or you can go ahead and just write Fe2 over Fe2O3 times 100. So we're going to have 2 times 56. It's 55.85, but we can round it to 56. We'll have 2 times 56 plus 3 times 16. So when we do our calculations there, we end up with 112 divided by 160. And we end up with 70%. (37), we want the percentage of bromine in the compound. So there are 3 of them. So this is Al here at the beginning for aluminum. There's not just an A on the table, so you know it's not an A and an I. So we'll go and we'll look up those values. Bromine is 79.9, so if you want to make it a little bit easier, just put 80. We have 26.98 for aluminum, so we can just make that 27 plus 3 times 80. So you end up with 240 on top and 267 on the bottom times 100. And that ends up getting us 90%. And to show it out to the ones place, we would put the decimal at the end. 38, we want the mass of oxygen in that compound, acetone. So how many oxygens are there? There's just the 1. We'll put it over the whole amount. So oxygen weighs 16. We're going to have 3 carbons, 6 hydrogens, and an oxygen on the bottom. So when we do that calculation on the bottom, we end up with 58. And we should end up with 27.6%. 39. We want the mass, the percent by mass of potassium in the whole compound. So we have 1K over KHCO3. So our potassium is going to weigh 39. We have 39 plus 1 plus 12 plus 3 times 16. So when we add all of those numbers up on the bottom for the whole compound, it equals 100 times 100, and we end up with 39%. For number 40, we have a compound that has a ratio of 1 copper to 2 chlorines. So that tells you your empirical formula right there. For 1 copper, you're going to have 2 chlorines paired up with it. Then we want to find the percent composition of copper and then the percent composition of chlorine. Once you find one, you can just subtract it from the 100% for the whole thing to get the other. So if we want the percentage of copper, we'll look up copper and we get 63.55. So then on the bottom here, we'll have 63.55 plus 2 of our chlorines, which weigh 35.45. So when we put that into our calculator on the bottom, we get 63.55 divided by 134.45 times 100, and we end up with 47% copper. So if the copper makes up 47% of it, all the rest of it is going to be chlorine, so just 100% minus 47% gives us 53% chlorine. For 41, we have some information about vitamin C. It has a molecular formula of C6H8O6, and it has a gram formula mass of 176 grams per mole. A gram formula mass is the exact same thing as molar mass. It's the values from our periodic table added together. So we don't have to do that step. It gives it to us in the problem. So we want to find the percent composition by mass of oxygen within that acid. So when we look at our formula, we have 6 oxygens over the whole thing times 100. So we'll have 6 times 16. You don't have to add up the whole thing. It tells you in the problem it's 176. So we end up with 96 over 176 times 100. And that is all you have to do on the problem. This is the correct setup. It just says, show a numerical setup. For 42, we have some information about different chemicals that are used inside of lights and the colors that you're going to see as a result of those. Our question at the end wants us to find the percent composition by mass of aluminum in the compound that produces green light. So out of the 3 compounds given, we have to choose the correct one, and it tells us that the compound that produces green light is this right here. So that's the one that we want to focus on. And we're going to include the correct numerical setup and our calculated result. So how many aluminums are in this compound? We have 11 of them. So we're going to have aluminum times 11. And on the bottom, we have all of these elements. And I know it's a little bit more than we're used to seeing all together like this. When we go and look up these values on our periodic table, one moment. Okay, we are going to end up with 26.98 for our aluminum, and we're going to have 11 of those. For CE, we get 140.12. Mg, we get 24.31. We have our 11 aluminums again and 19 oxygens. So we have quite a bit to add together there. So when we do our calculations, we get 296.78 grams on top for the aluminum, and we get 765.21 grams for that whole compound, times our 100 to change it into a percentage. So we end up with 38.8% aluminum on the coating that's inside that bulb. This last problem is going to be extra credit on your test. So I am not going to work it for you. If you would like to look through it and figure out the process before the test, that's fine. But I'm not going to work out a solution here for it.